Well, Unit 7 does have us using integrals and derivatives. It's sort of a little sidestep from the rest of the course. So Units 6 and 8, which border this one, are all about integrals and integral applications. But in Unit 7, we take a little temporary step to the side to talk about something slightly different, differential equations. While Unit 6 was the most tested unit on the AP test, Unit 7, this one, is one of the least tested. There will definitely be questions about it on the AP test, and of course we want to know the material, but hopefully that gives you a little bit of an idea that this is a slightly shorter unit, and you should definitely not be spending the majority of your energy and study time working on it. There are really just two things that we want to be able to take out of topic 7.1. The first is that the idea behind a differential equation is that it relates a function to its derivative. So let's say, for example, we're given the differential equation dp over dt is equal to kp. Notice here that what we have is p, which we'll say is population, for instance, and then we have dp over dt. Well, this is the derivative of p, or the rate of change of p. We could also write this as p prime is equal to kp. So we have an equation that's relating the original function p to its derivative p prime. We could also write this, let's say, as p prime of t is equal to k times p of t. This lets us see really clearly that p is a function of t. So we're relating the function p to its derivative function p prime. That's what a differential equation does. It sets up an equation that gives us a relationship between a function and its derivative, or a function and both its first and second derivative, and that lets us reason about all kinds of situations. So let's say, for instance, that we're told that the rate of change of, let's say, height of something, we don't know what it is, but the rate of change of height, well, we would write rate of change of height like this, is directly proportional to itself. Well, we would write that as k times h, and this would tell us that the taller the object is, the faster its height is increasing. We could also be told something like the rate of change of a train's position. So let's call the position of the train capital T. So the rate of change of the train's position, we'll say with respect to time t, maybe we're told that that is inversely proportional to the square root of time. Well, here's what that would look like. We would say k divided by square root t, because we were told inversely proportional to the square root of time. Whenever you're told that something is directly proportional, you want to put it in the numerator. When you're told that something is inversely proportional, you want to put that in the denominator. So this is really the second idea from topic 7.1, that we just want to be able to model differential equations. When we're told that something is directly proportional or inversely proportional, we want to be able to write equations like this and recognize that a differential equation is simply an equation that relates a function to its derivative functions. There are really only two main ideas that we want to take out of 7.2. The first is how to verify that an equation is a solution to a differential equation. So for instance, in this problem, we've been given the differential equation dy over dx is 2xy, and we've been asked to show that y equals 3e to the x squared is a solution. So this is just a procedural verification. We do it in two steps. First, we take this solution equation and we differentiate it. So we say dy over dx is equal to the derivative here, the 3 will stay, we'll get e to the x squared, and then we have to apply chain rule and multiply by 2x. So that's our derivative. And then our second step is to take this differential equation up here and substitute the solution equation in for y. Notice we've been given y is equal to 3e to the x squared, and we have a y up here. So we just plug it in. So we want to rewrite this as dy over dx is equal to 2x, and then instead of y, plug in 3e to the x squared. And what we see now is that we have two identical equations. dy over dx is 3e to the x squared times 2x. We have exactly the same here. And since they're both equal to dy over dx, we could take these right-hand sides and set them equal to each other to show that they are exactly equal. So we could write here 2x times 3e to the x squared is equal to 3e to the x squared times 2x, or if we wanted to simplify it on both sides, 6x e to the x squared is equal to 6x e to the x squared. And so that checks out, and we've shown that y equals 3e to the x squared is in fact a solution to the differential equation. So that's the first point to take out of 7.2. We want to be able to go through this verification process. The second point we want to take out is to realize here that there are an infinite number of solutions to a differential equation. And in fact, we can see that here. If instead of y equals 3e to the x squared, we had had y equals, let's say, pi e to the x squared, or maybe we would have had y equals negative 2e to the x squared. The idea is that we can replace that constant 3 with any other constant, and if we go through this same verification procedure, what we're going to see is that both of these are solutions to this differential equation as well. And the idea here is just that the general solution is y equals some constant c, e to the x squared. This is the general solution to this differential equation, where c can be any constant. So those are the two ideas from 7.2. Topic 7.3 is all about slope fields. And remember that a slope field is just something that we can use to estimate the solution to a differential equation. And it's really just a graphical representation of a differential equation on a finite set of points in the plane. So for instance, if we have a slope field that looks like this slope field is giving us information about the behavior of the function at different points in the plane. One thing you'll often be asked to do is match the correct differential equation to the slope field. And that's really as simple as plugging in or testing a few points. So for instance, if we need to pick which one of these differential equations is represented in this slope field, all we need to do is test a few points. So let's look here at our slope field. At the point 1, 1, let's choose that. We have a little arrow here near 1, 1 that's pointing like this. And so if we test the point 1, 1 in each differential equation, we should get, for the correct one, a slope that roughly matches the slope of that little arrow. So if we choose 1, 1, x is 1 and y is 1, here we get 1 minus 1 is 0. Well, that little purple arrow doesn't have a slope anywhere close to 0, so this is probably not our correct differential equation. For dy over dx equals x, if we plug in 0.11, we get 1. That arrow looks a little steeper than 1, but it could maybe be this differential equation. I don't feel like we can rule it out just yet. Let's check this third one here. At 1, 1, we get 1 plus 1 is 2. That looks more like a slope of 2, so I'd be leaning toward this differential equation, but let's test another point just to make sure. How about we take the point negative 1, 1, so we have this little arrow right here. Let's go ahead and test each equation just to make sure. So here at negative 1, 1, we would get negative 1 minus 1 is a negative 2. Well, that blue arrow definitely doesn't have a slope at negative 2. It looks like it has more slope of 0. So again, we rule out this equation. For this second equation here, at negative 1, we would get dy over dx equals negative 1. And again, that arrow has a slope more like 0 than negative 1. So it's looking like this one isn't going to be right either. We think it's this one, but let's go ahead and test. So negative 1 plus 1 is 0. And that does look like it has a slope close to 0. So this here is definitely going to be our correct equation. And we can continue to test more and more points to verify that this is in fact the correct equation. One other thing you can do is kind of look at a macro level. If we look at this slope field, we notice that every arrow in the first quadrant has a positive slope. And if we look here at this differential equation, when x is positive and y is positive, x plus y is going to give a positive value, which means everything in the first quadrant should have a positive slope, so that checks out. And here in the third quadrant, all of our arrows have a negative slope. Well, here in the third quadrant, x is negative and y is negative. A negative plus a negative is always going to give a negative value, which means every arrow in the third quadrant should have a negative slope. So this is really looking like our correct equation. And then you'll also be asked to go the other way. So for instance, with this problem, we've been given dy over dx equals 2 minus x and asked to sketch a slope field. The easiest way to do this is just to hold x constant and then solve for the value of the slope. Notice here that our differential equation is given only in terms of x. We have 2 minus x. There's no y involved in this equation at all, which means that the slope of our little arrow is only going to depend on the value of x. So here's what that looks like. Let's look at x equals 1, for instance. So at x equals 1, we're going to get 2 minus 1 is 1. So we get dy over dx, or y prime, is equal to 1. And because there's no y variable involved, regardless of the value of y, the slope is still going to be positive 1, which means that all along this line here, x equals 1, the vertical line x equals 1, our slope is positive. So if we were to sketch in little lines at each point, so 1, 1, 1, 2, maybe like this, 1, 3, we should be sketching in lines that have a slope of positive 1. So it might look something like this. If y was involved in the equation, we would have to calculate the slope for each y value, and it would change depending on the y value we chose. What about at x equals 2? Well, at x equals 2, we get 2 minus 2 is 0, so the slope y prime is 0, which means here that everywhere x is equal to 2, our slope is going to be 0. So we could sketch in something like this, and the value of y doesn't matter. And then at x equals 3, let's say, so x equals 3, y prime is going to be equal to negative 1. 2 minus 3 is a negative 1. So at x equals 3, we could sketch in a slope, something like this, about negative 1. And we could keep going. We could keep calculating values here at x equals 0, x equals negative 1, negative 2, negative 3 for these different values of y, and our slope field would really start to come together. So just make sure from topic 7.3 that you can match a differential equation to a slope field you've been given, and then use a differential equation to sketch its corresponding slope field. Topic 7.4 is just about getting more of an intuition behind the information that we can pull from a slope field. So for instance, let's say we're given this differential equation. So if you wanted to sketch a slope field here, realize that the only value that would matter is y, because we have no x over here on the right-hand side. So we could go ahead and find some values by holding y constant. So let's say that y is equal to 1. When that's the case, we're going to have 1 squared is 1, minus 4 is negative 3. We're going to end up with y prime equals negative 3 halves, or negative 1.5. Well, a slope of negative 1.5, everywhere where y is equal to 1, realize that the value of x doesn't matter because it's not included here on the right-hand side. So a slope of negative 1.5 might look something like this, everywhere that y is equal to 1. Again, the value of x doesn't matter, so we can just sketch this in. And then if we were to look at, for instance, y equals 2, at y equals 2, we get 2 squared is 4, 4 minus 4 is 0, 0 divided by 2 is 0, so we get y prime equals 0, and we could sketch in our slopes. The value of x, again, will not affect the slope, so we can just sketch a slope of 0 at each value of x along the line y equals 2. And now I'll go ahead and just finish off the slope field. What we can see now from the slope field is that we have two solutions to the differential equation. Because we have these horizontal lines here at y equals 2 and y equals negative 2, those are going to be solutions to the differential equation. And we can see that because if we say that a solution is y equals positive 2, and we plug that in to our differential equation, we get here 2 squared is 4, 4 minus 4 is 0, 0 divided by 2 is 0. So we get a value of dy over dx equals 0. But we also see that if we differentiate this solution, if we take the derivative of both sides here, we get dy over dx is equal to, the derivative of 2 is 0. And because here we get the same thing, we know that y equals 2 is a solution. The same thing happens with y equals negative 2. We would differentiate that to find that the rate of change at y equals negative 2 is 0. And of course, rate of change is 0 because we have here a horizontal line. And if we plug negative 2 into this equation for y, we end up with dy over dx is equal to 0. So we get matching equations. We know those are solutions. So we could sketch here a solution at this line and sketch a solution at this line. We can also see from the slope field here that curves at all other values of y are going to tend toward these two solutions. If we look here below y equals negative 2, we have this positive slope here, but we know that we're going to have this as a horizontal asymptote. So our curves might look something like this. We could sketch a curve here parallel to that part of the slope field, but then it's going to come and skim across the horizontal asymptote. If we come over here, we can sketch a curve, but again, it's going to skim along the horizontal asymptote this way. So we have those kinds of solutions below y equals negative 2. Above y equals positive 2, based on our slope, we're going to have curves that look like this, coming along this part of the slope field here, but then coming to approach the horizontal asymptote, the curve would look like this. If we come along this way, we're parallel, and then we approach this way along the horizontal asymptote. So this is what our curves would look like above y equals 2. But then between y equals negative 2 and y equals positive 2, we're getting something like this. If we start here at 0, 0, it looks like we're going to have something steep, but then it's going to start to shallow out and skim along our horizontal asymptote this way. And if we take the curve the other way, it starts to get more shallow of a slope, and we realize we're going to skim the horizontal asymptote this way. So based on what the slope field is telling us, we want to be able to reason about properties of these solution curves. For instance, if we're asked to find the range of the solution function that passes through the point 0, 0, well, we know if the solution curve passes through 0, 0, that it's going to be bounded here by positive 2 and negative 2. So the range of a curve passing through the point 0, 0 is going to be negative 2 to positive 2, not including negative 2 and not including positive 2, because remember, those are horizontal asymptotes, so our solution curve will get very, very close to those values, but not actually reach them. So the curve won't actually ever reach y equals negative 2 or y equals positive 2. So we have this open interval of negative 2 to 2. Similarly, for the range of a solution curve that passes through the point, let's say 1, 3, 1, 3, we know that's going to be bounded below here by y equals negative 2, so the range is going to be y greater than positive 2, not greater than or equal to, because we're not ever going to touch this horizontal asymptote, but the range is going to be y greater than 2. You could also be asked something like, what is the limit as x goes to positive infinity of a solution curve that passes through 0, 0? Well, that curve, as it heads toward positive infinity, is going to approach y equals negative 2. So the limit as x goes to positive infinity would be negative 2. But the limit as x goes to negative infinity, heading off toward the left of a curve that passes through 0, 0, well, that would be positive 2. So these are the kinds of questions that you want to be able to answer about a differential equation and its slope field. So just remember, if you're starting with a differential equation or the slope field, try to build out this model and get a visual in your head of what it looks like so that you're better able to answer questions about the behavior of these solution curves. The goal of topic 7.5 is simply to know how to use Euler's method to approximate the solution to a differential equation. So for instance, we might be given a problem like this one. Use Euler's method with delta t equals 0.5, or you might be told step size 0.5, to approximate y of 5 for this differential equation when y of 3 is equal to 0. And the equation that you really need to know for this is the y sub 1 equals y sub 0 plus f of t0 y0 times delta t. And the key here is to remember that we have these values here, so y sub 1 and y sub 0. This is an iterative process, which means that the approximation for y sub 1 is going to depend on the value of y sub 0. Y sub 2 is going to depend on y sub 1, y sub 3 is going to depend on y sub 2, etc. So we're always using the previous result to find the next approximation, which means that the more steps we take, the less accurate our approximation is going to be, because we keep taking an approximation of an approximation of an approximation. So we want to use as few steps as we can, but we also want to use the smallest step size we can. So this delta t value here, the smaller that value, the more accurate the approximation is going to be. If we take really big steps, we're going to get a less accurate approximation. So in order to solve these problems, which again is the primary goal of this topic, what you want to do is know how to build a table to estimate this y of 5 value that we're trying to find. You always need to start with whatever initial condition you've been given. So this initial condition tells us that t0 is 3 and that y sub 0 is 0. So you start building your table with your first t sub 0 value. So for us, that's 3. And then we're supposed to find y of 5 with a step size of 0.5. So we start adding 0.5 to this t value going down the column. So we say t1 is 3.5, and we're going to keep going until we get to 5, which is the t value we want. So t sub 2 is 4, t sub 3 is 4.5, and t sub 4 is 5. We've reached 5, which is the value we want, so we can stop. So we're going to have here 5 steps. Aligning with t sub 0 here in the next column will be our y sub 0 value, which we know from the initial condition is 0. Now we can start implementing here our formula. So we're going to say y sub 1 is going to be dependent on our previous two values, 3 and 0. So notice here that we're going to use the previous y, which ours was 0, so we get 0 here, plus then this f of t sub 0 y sub 0 means that we're evaluating our differential equation here at the point 3, 0, or the coordinate pair 3, 0. So we'll plug in 0 for y and 3 for t and get 0 minus 6, or a negative 6. So we could say here 0 minus 2 times 3, and then we multiply here by delta t, which is our step size of 0.5. When we calculate this, we get negative 3. Then we use 3.5 and negative 3 to approximate the next step here. So we say y2 is equal to the previous y, so negative 3 plus, and then here we plug 3.5 and negative 3 into our original differential equation. So we get negative 3 minus 2 times 3.5, and then multiplied by our delta t, and the value here is going to be negative 8. We keep going here, calculating a value for y sub 3. We're going to get negative 16. And then to calculate y of 4, we'll use 4.5 and negative 16, and we'll get a value of negative 28.5. So when the problem here asks us to approximate y of 5, we say that y of 5 is approximately equal to negative 28.5. And that's how you use the iterative Euler's method to find an approximation for the solution to a differential equation. The focus of topic 7.6 is just the procedure of solving a separable differential equation. Remember that we call it a separable differential equation because we can separate the variables. We can put all the y's on one side and all the x's on the other side. So for instance, given this separable differential equation, we've been asked to find the general solution. We need to obviously make sure that it's separable, and we do that by first recognizing that y prime can be rewritten as dy over dx equals y squared sine x. Because written this way, it's easier for us to remember that we can separate this. We can multiply both sides of this equation by dx, so we get dy equals y squared sine of x dx. And then remember, we want to separate variables, so we want to get all the y's on the left, all the x's on the right. we'll divide both sides by y squared, and we'll end up with 1 over y squared dy is equal to sine of x dx. So because we've managed to separate the variables, all y's on the left, all x's on the right, we know this is a separable differential equation. And now that we have our variables separated, we can solve it by integrating both sides. So we add an integral to both sides. Now we just need to integrate. So over here, instead of thinking about this as 1 over y squared, we'll think about it as y to the negative 2. Then our integral will be y to the negative 1, but then divided by negative 1, so we get a negative there. And then we say equals, the integral of sine of x is negative cosine of x. And then we add c only to the right-hand side. We don't need to add it to the left-hand side when we integrate, because if we did, those two constants of integration would eventually just collapse into the one single constant of integration, so we only need to put it on the right-hand side. If we multiply through both sides of the equation by negative 1, we'll get rid of the negative sign over here, leaving us with just y to the negative 1, which is the same as 1 over y, equal to, this negative sign will cancel, cosine of x, and then we'll get minus c. If we multiply both sides by y, we'll end up here with 1 is equal to cosine of x minus c times y. And then if we divide both sides by cosine of x minus c, we'll end up with y is equal to 1 divided by cosine of x minus c. Keep in mind here also that if you came out with this answer, you may also see it written as cosine of x plus c. And the reason is because if we left this as cosine of x minus c, just hypothetically, let's say we were given an initial condition and we were able to plug in and solve for the value of c. And we found that c was equal to 3, such that we had cosine of x minus 3, and that was our solution. Well, if we change this to a positive sign, what's going to happen is that when we go to solve for the value of c, we'll end up with c equals negative 3, and we'll still come out with cosine of x minus 3. We'll get the same result. So that's why you'll see in these problems that c simplifies a lot of the constants around it, because the idea is that when we simplify this value of c, we'll still always come out with the correct value for c. So just be aware that whatever answer you get, it might look slightly different depending on how you've rewritten this constant of integration, c. So as long as you know how to separate variables, integrate both sides, and then simplify the equation to solve for y and simplify that constant of integration, c, you'll be good to go on topic 7.6. Topic 7.7 assumes that you have already found the general solution to a differential equation. So in 7.6, we started with this differential equation here, which was a separable differential equation, and we had separated variables, integrated both sides, and simplified the equation to solve it for y, and ended up with this equation here. The idea behind topic 7.7 is simply that if we had been given, along with this original differential equation, some initial condition, so let's say we've been told that y of 0 was equal to 1, then once we get to this solution for the differential equation, we would take this initial condition and plug it in. So this says that x is 0 when y is 1. So we would say here 1 is equal to, plugging in this 1 for this y here. So 1 is equal to 1 divided by cosine of 0, because we're taking the 0 here for x and plugging that in here, cosine of 0 plus c. So we say 1 is equal to, cosine of 0 is 1, so we get 1 divided by 1 plus c. If we multiply both sides by 1 plus c, we get 1 plus c is equal to 1, and if we subtract 1 from both sides, we get c is equal to 0, which means that this general solution becomes a particular solution, which we'll write as y equals 1 divided by, and then we'll plug 0 in for c. We'll get cosine of x plus 0, or just cosine of x. So what we say then is that this on the left here is the general solution to this differential equation, and this on the right is called the particular solution to this differential equation. The idea is that the general solution represents an infinite number of solutions because C just represents any constant. So C could be 0, it could be 1, 2, 3, it could be pi, it could be E, it could be any constant. So this general solution is an infinite number of solutions to this differential equation. It represents the entire family of solutions. But once we have this initial condition, then we're saying we want the single solution from this general family here that passes through the exact point 0, 1, right? This is x equals 0 right here and y equals 1. So this is the ordered pair here, 0, 1. So we're looking for the particular solution that passes through 0, 1. In other words, if you think of the slope field represented by this differential equation, we're looking for the specific curve that's going to pass through 0, 1 in the xy coordinate plane. And that curve specifically is given by the equation y equals 1 over cosine of x. So if we graph this curve on top of this slope field here, this curve is going to pass through the point 0, 1 and satisfy this slope field. That is the particular solution that passes through the point 0, 1. So the takeaway here is just the idea of taking your general solution, plugging in an initial condition, and winding up with a particular solution, which is one specific solution that happens to pass through a specific point in the slope field. Topic 7.8 is about modeling exponential growth and decay functions using a differential equation. And the key takeaway here is this relationship. When we have a differential equation given by dp dt is equal to kp, what this is really telling us is that the rate of change of p with respect to time, and we'll say that p is population, that's most commonly how we refer to p, but you could also have dy over dt, and it doesn't necessarily have to be a population, it could be some other value. But this is saying that the rate of change of the population with respect to time is proportional to the number of, let's say, people in the population. In other words, this equation would tell us that, let's say we have a 10% growth rate in the population. This is saying that rate of change is proportional to the number of people we have in the population. So if our population is 10 people, then the growth rate is going to be 10% of that, or 1. So the population is going to be growing by 1 person per unit of time. But if we have 100 people in the population, then 10% of 100 is 10. At 100 people, the population is going to be growing by 10 people per unit of time. So this k value is just the constant of proportionality. And when we write the rate of change equation this specific way, k times p, it means the rate of change of the population over time is proportional to the number of people in the population. And whenever you have a differential equation in this form, the general solution is always going to be given in this form, y equals c e to the kt. Notice that same constant of proportionality. And we've already seen how to find this. This solution comes directly from solving this differential equation as a separable differential equation, separating variables, integrating both sides, and then solving for y. If you do that with this equation, you're going to get this general solution. One thing we want to note about this solution here is that this value of C is initial population. So that is the population at time t equals 0. And that makes sense because if we substitute t equals 0 into this equation, we get k times 0, that's 0, e to the 0 is 1, we just end up with y equals c. And remember, y models population. In fact, because we've written this differential equation with p's, let's go ahead and write this with a p. So we're really saying that the population is going to be equal to c when t equals 0, which is why c is the initial population. Again, sometimes you'll see this written as dy over dt equals ky, and then over here your general solution would be y equals ce to the kt. So you just want to understand this relationship. You want to understand that this equation is the general solution to this differential equation, and in order to find a particular solution, we need some kind of initial condition, or we need to know the population at a certain time in order to solve for that value of c. We also want to be able to visualize this kind of growth rate. The idea here is that we have exponential growth. So if we were to graph a population that follows this model, then the growth rate is going to look something like this. It's going to start here at 0, and then it's going to increase exponentially like this and continue growing exponentially. So this is the picture of the growth rate associated with this differential equation and its solution. So let's think about an example here. Let's say that we know, for instance, that a beehive is dying. So we have exponential decline. And we're saying that the number of bees is decreasing at a rate proportional to its population. So if we call the population capital B, we would say that the rate of change of B is going to be proportional to the number of bees in the population. And then let's say we've also been told that before the population began to decline, so we'll say at t equals 0, like this, the population of bees was 5,000 bees in the hive. And let's say we know also that after 3 months, so we'll say t is in terms of months, so after 3 months there are 4,500 bees in the hive, and we want to figure out how many bees are left after 1 year. Well, we could solve this step by step as a separable differential equation, but we already know the solution over here is going to be B is equal to CE to the KT. We know C is equal to 5,000 because we're told that at time 0, B is 5,000, but we could solve for that. We could say 5,000 is equal to CE to the K times 0. K times 0 is 0, e to the 0 is 1, so we get C times 1 or just C, so we get 5,000 is equal to C. And so then we could write our equation with our initial population here as B equals 5,000 e to the KT. Then we use this other condition we've been given to solve for the value of K. So this time we say that the population of bees is 4,500 at time 3, so e to the 3k. If we divide both sides by 5,000, we get 9 over 10 is equal to e to the 3k. And then to solve here for k, we want to take the natural log of both sides. So natural log of both sides, because that'll cancel out the e. And so we'll end up with 3k is equal to natural log of 9 over 10. And then we divide both sides by 3. So we get k is 1/3 natural log of 9 over 10. Now we have this value for k, and so we can write over here an equation for b. So we'll say b at time t is equal to 5,000 e to the 1/3 natural log of 9 over 10 multiplied by t. Notice now that we've solved for c and we've solved for k, and so we have an equation, b of t, that's going to allow us to take any value for time and plug it into this equation and find the population of bees at that time t. So if we want to find the population of bees after 1 year, remember that t is in months, so we need to plug in t equals 12. So we would say that b of 12 is equal to 5,000 e to the 1/3 natural log of 9 over 10 multiplied by 12. We'd use a calculator to find that value, and that's going to tell us how many bees remain after 1 year. So in topic 7.8, we talked about modeling exponential growth with a differential equation, and we said that if a population grows proportionally to the number of people or subjects in the population, we model that with this differential equation. And we said that a general solution to a differential equation in this form was given by this equation here, where the initial population is given by C. So at time t equals 0, the initial population is C, and that goes right into this general solution. And if we have another condition, if we know the population at a specific time t, we can plug that in, solve for the value of k, and get a particular solution for the differential equation instead of just this general solution. And this situation models exponential growth. So we have here exponential growth where over time t, the population p grows exponentially. And the idea here is that this population grows exponentially without any restriction. So you can imagine a population where there's unlimited space, unlimited food, no predators, nothing to stop this population from multiplying unbounded, unrestricted. And when you have that kind of situation, you have exponential growth. But of course, as you can imagine, many populations grow with restriction. There might be a shortage of space, a shortage of food. There might be predators in the environment. There are things that restrict the rate of growth of the population. If you can imagine the number of people on Earth, there's only so much space on Earth. There's only so much food and water on Earth. And so as the human population grows, you can imagine that we run into what's called carrying capacity, where at a certain point, we can't sustain our population above a certain threshold. And so we kind of have this upper boundary past which our population doesn't grow. That's the carrying capacity of our environment. And when we have a situation like that, where there is restricted growth, where there's some kind of carrying capacity that is preventing a population from growing exponentially, we model that with a differential equation in this form instead. So in this situation, notice how we have the same Kp value as we did over here in exponential growth. But then we've multiplied it by either a minus p or 1 minus p divided by m. These are just two different ways of writing the same thing. And adding this extra binomial to the exponential growth equation is what's going to restrict the growth. So you can imagine here, if we have a population, let's say that our carrying capacity is this value right here. We'll call it either A or M. A if we have our equation in this form, M if we have our equation in this form. This is carrying capacity. And so we'll go ahead and draw a line here. Let's say that the population can't really grow beyond this value because this is the point at which we start to run out of food or run out of space and the population growth gets restricted. This is called the carrying capacity for the population. We can see what happens here if the population hits this value. So in this first equation, if the population P reaches this level of A, then we can say P equals A. We would get A minus A here, which would be 0, and this whole term would be 0. So the result, if P gets to A, if P equals A, then what we end up with is dP over dt is equal to 0, or the growth rate of the population is 0, meaning it's not growing at all. It's also not shrinking, it's just staying stable. It's stable at that value, it stays the same. Similarly here, written this way, remember this is exactly the same equation as this one, it's just a different way of writing it, and you'll see it both ways, which is why I wanted to mention both. But when we call the carrying capacity M, and if we say that the population reaches its carrying capacity of M, then we say P is equal to M or M is equal to P. So here we would get M divided by M, which is 1. 1 minus 1 is 0. And so this whole term becomes 0. And the result then is the same thing. We get dP over dt is equal to 0. The rate of growth or the rate of decline of the population is 0. The population is not growing, it's not decreasing, it's staying the same here at 0. Because that's the case, if we want to solve for carrying capacity in a population, all we have to do is set the rate of change equal to 0. Notice here that we got rate of change equal to 0 in both cases. So if we set rate of change equal to 0, then we're able to solve for A or solve for M, and that's going to give us carrying capacity. So for instance, let's just say that we're given a differential equation in the form, let's say dP over dt is equal to 0.2 times P times, let's say, 2 minus P over 500. And we want to find carrying capacity. Well, all we have to do is set the rate of change equal to 0. So 0 is equal to 0.2 P times 2 minus P over 500. Well, we know here we have two factors multiplied together. So we're going to have two different scenarios where this is true, either this scenario or 2 minus P over 500 equals 0. This first equation makes sense. This is going to be true when P equals 0. And of course that's true, because if the population is 0, then the rate of change is going to be 0. If there are no people in the population to reproduce, the population will not be either growing or declining. It's going to stay stable at 0. So we kind of have this second solution here at this point where P is 0. In this solution, we add P over 500 to both sides, and we get P over 500 is equal to 2. Multiplying both sides by 500, we get P is equal to 1,000. And so we would say that our carrying capacity for this particular differential equation is going to be 1,000. And so we can maybe put this up here, 1,000, and this is 0. What this looks like then, in terms of the curve that models the population, remember this was the curve that modeled exponential growth. Well, a curve that models restricted growth here is going to look something like this. Well, we're going to start here at 0, and at first, growth is going to look exponential because we're going to have plenty of resources and no restriction. But then as we get close to carrying capacity, growth is going to start to level off something like this and approach carrying capacity as a horizontal asymptote. What this means practically is that growth is going to be maximized right at this point here where the curve changes concavity, where there were still plenty of resources and the population really got going, but before the population started to be limited by the resources that are imposing this carrying capacity. So in order to find that maximum rate of growth of the population, that's always going to be at half the carrying capacity. So if carrying capacity is 1,000, then when the population is half of that, which is 500, when the population is 500, that's when the rate of growth, dp over dt, is maximized. So the rate of growth is maximized when the population reaches exactly half of its carrying capacity. So the whole idea here is just to be able to compare and contrast exponential growth versus restricted growth to know the differential equation that models each one. And then especially when it comes to this logistic equation, the restricted growth model here, this differential equation for restricted growth, is called the logistic equation or the logistic model. For a logistic equation, to be able to find the zeros, meaning to know that the population is stable at 0 and stable at the carrying capacity, to be able to find that carrying capacity, to know when rate of growth is maximized, and to know, for instance, that as we take the limit as t goes to infinity of this blue solution curve here, that we're going to approach carrying capacity because we have this as a horizontal asymptote. So we just want to be able to intuitively make conclusions about this logistic equation. Okay, so that's it for Unit 7. You really want to make sure that you know how to model with differential equations. So given the description of a scenario, you want to be able to write a differential equation that models that scenario. You also want to be able to match differential equations to slope fields. So given a differential equation, you want to be able to sketch the slope field. Given a slope field, you'd like to be able to identify roughly which differential equation is associated with that slope field, and you want to be able to reason using slope fields. You want to be able to approximate the solution to a differential equation using Euler's method. And then you want to be able to find general and particular solutions to separable differential equations. So you want to solve the separable differential equation by separating variables, integrating both sides, and solving for y to give you a general solution, and then be able to plug in an initial condition or some other condition in order to solve for the particular solution. And then lastly, you want to be able to solve and interpret both exponential and logistic differential equations. So given a differential equation in the form of an exponential function or the logistic equation, you want to understand what exponential growth looks like versus what logistic growth looks like that is restricted by some environmental factor, and be able to solve for things like carrying capacity, maximum rate of growth, etc. Once you're good to go on Unit 7, make sure to come back and move on to Unit 8, where we'll dig into applications of integrals.